So the next topic is scoring systems. And scoring systems have been used for about 100 years in criminal justice. This is the Burgess model from 1928, and it's pretty funny. So it would add up points for various aspects of your criminal history and then translate into some risk of success or failure on parole. Obviously, this isn't a machine learning model. It's not data-driven exactly. And they grouped people into interesting categories like mean citizen and ne'er-do-well and recent immigrant. Obviously, these kinds of scores wouldn't be used today. And in fact, there's a lot of debate about the fairness of risk scores in criminal justice. There's been a lot of studies, criminological studies about risk scores, and what they found is that they tend to be less biased and capricious than judges. They can be held accountable for bias, and also they tend to reduce incarceration. But again, these are all up for debate. So anyway, here's a more recent risk score. This is a Pennsylvania Commission on Sentencing score, and again, it's a point score. So you add up points and then translates into your risk. And then this is the Violence Risk Appraisal Guide, and here you add up the points and then it translates into low, medium, and high risk. And then in medicine, there are huge numbers of these risk scores, huge numbers, and they're broken up in this website by the different field of medicine. So for instance, if you go look at seizure risk, you can find the 2 helps 2B score, the one that we talked about earlier. And then if you click on it, it brings up a screen where you can fill in the information in the form and it calculates your 2 helps 2B score for you. It tells you how many points you get for various things. Now, there are 2 types of risk scores that I want to discuss. There are decision-making scores, decision-making models, and risk scores. So the decision-making models, the points get added up, and if they're above a threshold, then you predict, high risk and then otherwise low risk. Whereas in the risk score models, then the total score gets translated into a risk using the table at the bottom. And both are valid types of models for different applications. Now, the key challenges in designing these risk scores are that people might want to add constraints to them. For instance, if you want to make sure that your medical scoring system doesn't have more than a 20% false positive rate, then you have to put that extra constraint in there. And also, like if you want to make sure that your scoring system is fair to certain groups and so on, you want to be able to build that in. And then as well, because you want the scores to be integers, you have to build that in the design of the risk score. So the typical approach, unfortunately, is that people just get a bunch of experts in the room, like physicians or something, and then they decide on the score, and then that score is evaluated afterward using data. So there's no data that goes into the formation of the score, it's just used for evaluation. Another typical approach is to have a domain expert select the features for the model and then do logistic regression and then scale the coefficients and round the coefficients. And that's one way to get a model. The only problem with that way of designing models is that that type of rounding can really go against the performance gradient. So for instance, if we had 2 coefficients, coefficient 1, coefficient 2 on the axes, and we're trying to minimize the logistic loss, but we still want an integer, scoring system, which, the integers are very important. People go to a lot of lengths to make sure that these scores are integers because it's much easier for people to understand logical arguments when they're made in terms of integers than if they're made in terms of real numbers. It's much easier to sort of mentally do those calculations in your head and try to understand, well, if I change this thing, what would it change my score to, and so on. So anyway, if this is this is a contour plot of the logistic loss, then we want to be able to round. We round, and unfortunately now the loss goes up a lot. But as it turns out, there was a much better solution, that one over there, where we would have kept our low loss and still managed to get integer point scores. So rounding can be dangerous, and this actually does happen. So I'm going to give you an example where we start with an elastic net model this is a seizure prediction. So the same task as the 2 helps 2B score. So we're predicting seizures in critically ill patients. And we start with an elastic net model, and we're going to just round. So what happens when we do that is that all the small coefficients get rounded to 0. So you've wiped out a huge amount of the signal there. That's probably not so good. So then we're going to try rescaling the coefficients and then rounding them. But what do we scale it to? And if we scale it very high, then when we round, we get point score values that are really large, like 10, and like sometimes you could get 52 or something, depending on what happens when you do that rounding. So, so that's not so good. And then also, what if you want to incorporate constraints like these fairness constraints or the false positive constraints? I mean, how can you do that when you're scaling and rounding? Like rounding, it won't obey the constraints. So on the other hand, if you used an algorithm that could take care of all that stuff together, you might get a very small, like a very sparse risk score with low, point values that actually is pretty good. And this is an example of of a score that came from an algorithm called RiskSlim that is better calibrated than the other scores I just showed you and has a large area under the curve. And it also could, this algorithm can accommodate constraints if you want to add them into the model. Okay, so as I mentioned, the typical approaches are either a panel of human experts or a lot of manual work, choosing features, scaling, rounding, logistic regression coefficients. Now, there are some modern approaches that don't seem to have these problems, as I just mentioned. So there are some specialized techniques for rounding, but they're not guaranteed to produce solutions that are optimal in any sense. But they are better than just plain old rounding. And then there are also mathematical programming tools that can satisfy some of the constraints that you care about. Okay, so that works for the decision-making tools, like where there's a threshold. But then if you want to talk about the risk scores, then things get nonlinear and the optimization problems get much harder. So you can still do rounding, but then the tools that you might want to use are more, if you want to fully optimize for the risk scores, then you need to go to some more sophisticated techniques like cutting planes with branch and bound. And like I just showed you that solution from RiskSlim a minute ago. And that was created with this kind of cutting plane branch and bound combination. Okay, so let's talk about the modern approaches for the decision-making tools. Now, this is a formulation. This is one of many formulations for the decision-making tools. Okay, so here there are 3 terms in the objectives. The first term is accuracy. So make the model accurate. And you could use weighted accuracy, or if you cared about a different performance measure, that's fine too. So make the decision model accurate, and then make it sparse by adding L0 regularization, which just counts the number of non-zero terms in the model. And then there's a third term, which is an L1 norm. Now, usually L1 norms try to influence sparsity, but here, as long as epsilon is sufficiently small, the L1 term does not influence sparsity whatsoever. The only thing it does is make the coefficients co-prime. So we have some constraints below also that say that the coefficients have to be, integers here between -10 and 10, but you can choose what you like. Okay, so this co-prime coefficient term, what it does is, so if you, for instance, run minimize this thing without that L1 term, then you could get coefficients 2, 2, 4, 2, and 6, which are clearly not co-prime, right? So if you add this small L1 penalty, then it will say, among all equally good decision-making solutions, I'm going to choose one where the coefficients are co-prime. So it'll reduce it to 1, 1, 2, 1, and 3. Okay, so there's no prime factors in common. And in fact, and you can add additional constraints if you want, like the false positive constraints or the fairness constraints. And then I just want to make a remark that, as long as epsilon is small enough, as long as that epsilon is sufficiently small, then this optimization problem produces a scoring system with co-prime coefficients. And the co-primeness there provably cannot interact with the sparsity or accuracy. You're never going to sacrifice accuracy or sparsity to get co-primeness as long as epsilon is below this particular value. Okay, and then again, this goes into the mathematical programming solvers, and then they can solve the problem pretty quickly, although of course it's not as fast as if you sort of did least squares, but of course these are problems you can't do with just matrix inversions and so on. But here in this case, this is a linear modeling problem. This isn't like decision trees. Here we're trying to create a linear model, and this is a linear programming solver. So it's a much better match of the solvers to the actual problem at hand. Okay, so let me tell you about the risk assessment tools, and specifically, this is the formulation for the risk slim algorithm, which again produces risk scores, and those risk scores aim to be calibrated to the data. So here, the terms in the objective are the logistic loss, which produces a good calibrated risks, and then a model size term to keep the model sparse. And then there's the additional constraint, which is that, again, each of the coefficients has to be an integer between negative 10 and 10 if you want to. And then, of course, you can add additional constraints if you like. Okay, so this, of course, is a really hard problem to solve. This is a mixed integer nonlinear program. It's really hard, and there's no solver that can solve this problem by itself in a reasonable period of time. So for this kind of problem, you need a specialized optimization technique. And that kind of explains why in the past people would do a lot of manual feature selection for scoring systems. So let's just pretend for now that we're just dealing with the logistic loss, okay? So we just want to minimize the logistic loss, but we want to minimize it over the integer lattice, okay? So we want the coefficients to be integers. Now, what this kind of method does is it iteratively computes an under approximation to the loss function. You can see it's labeled cutting plane approximation here. So it's this sort of piecewise linear under approximation, and that approximation gets better and better as iterations continue, because there are more and more pieces that are added to this approximation. And at each iteration of the optimization procedure, it solves the linear program that minimizes this cutting plane approximation. So you would find that solution here, but then you suddenly realize it's not integer, and so then actually you say, oh no, what am I going to do? Because I need a solution where the coefficients are integers. So what you do here is you actually realize, okay, I can't have a solution like this. And in fact, I cannot have any solution between 5 and 6, okay? So you literally ban that whole area by saying, okay, the coefficient I got here is 5.5. I'm going to subdivide the problem where I create one subproblem where I add the additional constraint that the solution has to be less than or equal to 5. And then I add another subproblem where I say, okay, the solution has to be bigger than or equal to 6. And so this forbids that coefficient ever from becoming anywhere between 5 and 6. And then you continue to run the algorithm, and you add more and more of these constraints and create more and more subproblems until eventually you get an integer solution that is the answer to this problem. And this actually seems to work reasonably well to the point where you can actually solve pretty decent sized problems with this type of technique. Okay, so let's go back to rounding. Let's say you don't have the resources to try to figure out how to use all these complicated techniques and you just want to do rounding. So let me show you some of the clever rounding techniques. So this technique is called sequential rounding. So let's say that you start with your logistic regression solution, and then instead of just rounding all the coefficients at once, what you do is you round only one coefficient. And you round the coefficient that does the least amount of damage to the loss function. So the loss only goes up a little bit when you do that rounding. And then here I've rounded down because I actually did less damage to the loss rounding down than I would have done if I rounded up. And then I keep doing that until all of my coefficients are integers. And so from there, I don't use that solution. I'm going to run another algorithm called discrete coordinate descent. And what this algorithm does is it adjusts the coefficients it adjusts the coefficients to minimize the loss. So if you start here, then discrete coordinate descent would pick out which coefficient I could edit so that I would reduce the loss the most. So here it's saying I should change that 1 to a 2 because that reduces my loss the most. And I should change that 1 to a 4 because that reduces my loss again. And then you keep going until there's nothing you can improve. And that is called a one-op solution. This is a solution that is optimal with respect. It's a locally optimal solution to the point where you can't adjust any coefficient and make the solution better. So that's why it's one-opt. Okay, so that covers the sort of range of approaches to these scoring systems, as I mentioned. And let me give you a sense of what I think the future approaches to this problem ought to be. So first of all, the mathematical programming approaches are difficult to use by people who are not familiar with it. So these techniques need to be much easier to use by scientists, by doctors, by whoever wants to produce these scoring systems. And these are like human interface, human interaction issues, as well as statistical issues and optimization issues. Also, again, these problems are hard computationally, so it'd be good if we could improve their scalability. And then they also have trouble handling continuous variables. They usually have to break continuous variables into like many, many binary variables, so that's not so good. And then right now, these algorithms have very good finite sample bounds, but there are many that help with generalization error and good out-of-sample error, but there are many, many statistical issues to consider. Okay, thanks.